Welcome back after the break. This is the main seminar. We are very happy to have Sebastian Halbig from Marburg, and he's going to speak or give us a non-semisimple Kitaev lattice model. Please.
Okay. Hi. Thank you very much for the invitation. It's great to be in Prague. First time being at the Charles University. And yeah, I'm going to pick up basically where we left with the pre-seminar. And so what I'm going to tell you is I hope it's a fun project. And there's a lots of still open questions. So see this half as a talk on results and half as a pitch for things you can do in your research if you find this kind of maths interesting. And I'll try to highlight some of these questions and possible points where you can try to generalize, work out examples and so on. Because it's quite fun. If you want these slides, by the way, you can scan this QR code and get the slides here. So without further ado, what is the whole story about? The whole story is about this model for quantum computation, but it should be fault tolerant. We want to look at these topological states. And what we saw in the pre-seminar is that following global point of view is you have some combinatorial datum, which were these graphs you've seen in the pre-seminar, and you want to use them in two ways. You want them to parameterize some topological information, and you want to use them to define representations. This was where the L and the T operators came into place. And now you have two things which might or might not have something in common, and obviously you're interested because they should have something in common. And the aim is to find this this common thing, which is this protected space, the ground state of the Hamiltonian, for example, was this invariant subspace in the classical model. And now we need, in the non-semisimple version, we want a different story to arrive at the space, which is more inspired by algebraic topology. Okay, that's the wrong direction. Let's continue. So let's take a step back, and I want to repeat briefly the story which we saw in the pre-seminar, because I think it's quite instructive to see this a few times. At least I found it quite instructive to finally get the hang of the model. So let's see in the easiest example what's going on. Okay. So what we want to construct, right, is the ground state of the Hamiltonian. That's what we're after. We're not after universal quantum computation and all the additional things which would now come after we've defined the space. We just want to construct the space. And how does this work? Well, as a first step, we take a k by k lattice on the torus, and we define this Hilbert space, which is just the assembly of the spin states we're looking at. Then we will define this Hamiltonian. Yeah, that's what is it? 2 times k squared copies of c squared.
Direct sum of two
tensor product, but yeah.
Tensor product.
Yeah,
it's tensored over.
Tensored over c, or the complex numbers. But we're tensoring c squared, so it's not very
okay.
It's not a convoluted way of telling you I'm working with the complex numbers. It's a bit more than that. But we'll see in a second. The point is, so we will construct a space, we will define a Hamiltonian, and this Hamiltonian, as before, it was just an assembly of these L and T operators in some funny way. So it's very much just seeing local structure. However, if we then look at the kernel of the Hamiltonian, we get this protected space, and it somehow now sees global structures. And this is why we get this error correction. In a mathematical term, all of this means for us, you can give me any number k, whatever you're giving me, the kernel will always be a 4-dimensional space, independent of the number k, which is quite odd that you can build all of these representations and the invariance of space is always 4-dimensional. Something interesting is going on. So let's again look at the easiest example, which we already saw in the pre-seminar. Let's look at the toric code, really, the model for the group algebra of the cyclic group with 2 elements. So we take the torus, and as we did in pre-seminar, we cut this open and say, okay, we view this as a lattice with periodic boundary conditions. And for every edge in for every edge in the torus and lattice, we take a copy of c squared, which now gives us our extended Hilbert space, or our Hilbert space is just this big tensor power of c squared. Some huge vector space, potentially huge vector space. And now we want to give it some algebraic structure. So we notice two things. The first thing is our lattice set has points. I want to call them vertices from now on. And for every vertex, where is it here? I choose this Pauli matrix, sigma x, and each vertex has 4 edges next to it. And I'm applying this Pauli matrix to these 4 edges. And every other edge, I'm doing nothing. I'm acting by the identity. Now, this Pauli matrix, as any other Pauli matrix, squares to the identity. So I can think of this whole thing as a group representation, or as a representation of set 2 on the extended Hilbert space. All of these actions commute, so I can summarize all of these actions in a global picture and say I have a vertex action given by a certain tensor power of my group algebra acting on the extended Hilbert space. That's good. That's sort of the A operators are hidden in this picture. Let's continue from here. Besides points, my lattice has squares. I want to call them faces from now. And again, I'm choosing a different Pauli matrix, sigma set. And for all of these 4 edges at the boundary, I'm applying sigma set on the boundary. Again, this gives me a linear map, right? Everywhere else, I'm doing the identity, so this gives me a linear map on the extended Hilbert space. It squares to the identity. Again, this is a representation of the group set modulo 2 set. Great, but this is self-dual, the Hopf algebra of the cyclic group with 2 elements. So I can think of this equally well as a co-representation, just for the fun of it. No? So I have a representation, I have a co-representation, and as in the representation theoretic side, all these co-actions commute. I can think of a global phase co-action. And now I can ask the question which anybody who does Hopf algebras should ask at this point. I have an action, I have a co-action. What is the commutation relation between those? And that's where the Drinfeld double enters the world, enters the story by this Drinfeld module structure, which is a different way of saying it's a module over the Drinfeld double because we're working here with finite dimensional Hopf algebras. To make the vertex its favorite adjacent face. Here I've chosen the rule that I will always go top right, but I could make any other choice. And then you work out that the action of this vertex and the face to its top right, they precisely satisfy the commutation relations of a Jetter-Drinfeld module. This forms now, these operations now give you a module over the Drinfeld double of this group algebra. And just to break this down, this really means it's an action of the Klein form, because we're in such a simple case. It's very easy. These things commute. That's all there is. But why I'm saying this? Well, this now gives us a very, very nice way of summarizing the global picture of the model we've constructed so far. We have this big vector space. We have a module structure over the Drinfeld double of some tensor power of the Drinfeld double of the cyclic group with 2 elements. And we can define what was the kernel of the Hamiltonian now as just the invariant subspace of this module. And it turns out that, as I said, and there's various ways of proving that here, as we've seen in the pre-seminar. Basically, all these proofs use the Haar integral, so you can explicitly construct maps between the extended Hilbert space labeled by some number k and k+1, and you can check by using these projectors coming from the Haar integrals that these maps are isomorphisms on the invariant subspaces.
Just to clarify, so this M-inf is now really the space of all elements that are invariant under the action of the double.
Yes.
Okay.
Yes.
Where the
yes.
action equals epsilon.
Yeah.
Okay.
Yeah.
Thanks.
And it's really the action of the double. So they are trivial as a co-module and trivial as a module. That's the point.
So how would this read in terms of the Drinfeld modules? So is it invariant under the action and the coaction? Or?
Yes.
Oh, okay.
Let's see. So a different way of saying this is this space, did I put a K? Yes. Is the set of all M in my extended Hilbert space with the property that if I take the coaction at a face of M, I'm simply getting one tensor M. And if I take the action with respect to some vertex on M, I'm acting by the co-unit. And this is for all M in, I don't have to add, this is for all H in my Hopf algebra, which here just is the group algebra of Z. And for all faces and for all vertices.
I quite like that because usually one looks at invariance under some action or some coaction, but here you really ask both things at the same time. Okay.
Yes.
Yes.
And yeah, it's quite surprising. I mean, you can ask this for any module. What's the invariant subspace? You would not expect that you take completely different modules somehow. They are all the same space essentially. They're all at least of the same dimension. And in fact, there are nice maps going between those. So something deeper is going on. And we want now to take this picture and work out what happens if you remove semi-simplicity. What this means is we have to change basically everything we did so far. So we will not talk about lattices anymore. We will replace them by certain graphs, which we've already seen hints of in the pre-talk, pre-seminar, which we want to propose to call Kitaev graphs. Now, what we had on the edges were C squared, which is the same thing as a vector space as my group algebra. And we've seen in the other talk that this is really about multiplication and co-multiplication of the group algebra. Also, this we have to change completely. So we will introduce this notion of involutive twisted Hopf bimodules. And then these invariant subspaces don't quite do the thing we want them to do. So we have to do a more advanced, strange construction, which will be these bitensor products, which combines the tensor ring over an algebra with cotensor ring over a co-algebra. So let's get started. What are these Kitaev graphs? The role of these Kitaev graphs is to parameterize surfaces. And essentially what they are finite connected graphs. I can have loops, as you can see here. There's a loop. You could have multiple edges between vertices, which is not shown in the pictures. Every edge has a direction. And then there's these funny things which I don't count as edges, these red lines, and they do multiple things for us. The first thing is, whenever I have a red line, because this is now drawn on the plane, I get a nice total ordering using the counterclockwise orientation of the plane at the really just the edge ends near my vertex. So I can move counterclockwise and say, okay, first I'm encountering this edge here, and then I'm encountering this edge here. Yeah. Moreover, these red lines, they point into some face. You can see this thing here has 3 differently colored regions, which we want to call faces. So this gives me a nice bijection between vertices and adjacent faces. I want to call this cilia in the remainder of the talk. And finally, I made a choice which is completely arbitrary, but I said the vertex here at the bottom, this is my favorite vertex. This is my best friend for now. And I'll always pick that guy. You can pick anyone you like, but you make a choice which is your favorite. Okay, now let's see why we want to use these graphs, what they have to do with topology. This picture is not too scary, but I later realized it's probably very complicated, but it's also quite tedious to make these pictures, so I didn't change it. Sorry for that. So we take a Kitaev graph gamma, which is here on the left. And now, in the first step, what I can do is I replace every vertex by a small disk and every edge by a small ribbon. You know, really a rectangle with 2 short and 2 long sides. And what happens is this is now a oriented surface with boundary. Sorry, as you can see here. And what are boundaries? Well, boundaries are just closed curves, right? This is a copy of something homomorphic to S1. So I can take a disk and I can glue my disk to the boundary. And if I do this, I close all the boundaries, so I get now a closed surface, which is happening here. So my graph on the left was describing here a torus with 2 boundary components. closing these two boundaries. One is the inner one, which you can see here at this black vertex, and one is the outer one here, which is not really that well visible. If you close these two boundaries, you get just the torus. Now, obviously, I could have drawn a different graph on the torus, for example. The standard generators of the fundamental group would have been fine. They both give me homeomorphic surfaces. So there's some question about which graphs give me homeomorphic surfaces. And let's try to understand how this works. And the thing you can realize is that you can do sort of elementary transformations on these graphs, which change the graph, but not this homeomorphism class of the surface. The first one is a rather trivial observation. I mean, the topology does really not depend on the direction of the edges. So you should be allowed to flip the direction of these edges. This is purely combinatorial datum, which we'll use to define the representations. A more subtle operation, if I have two edges, one the yellow one and the other one the blue one, I can slide one edge along another. And this will, again, not change the homomorphism class of the surface. And this is a bit more interesting to see. And at least these pictures indicate that you should be able to go from left to right and from right to left. There should be some kind of invertible structure. And if you have this, you can think, probably there's a group action modeling that. That's precisely what you can find out. These elementary transformations, they give rise to this structure group G, which acts on the set of Kitaev graphs. And it's a very nice action. It does not, however, classify surfaces without boundary, closed surfaces, because both of these actions do not change the number of boundary components. So we need one more ingredient, and that's the realization put here on top of the slide, is I can take a certain graph, the annular graph. I can draw it here. It looks like so. It's just a loop and a spike pointing into the loop. I can attach the annular graph to some other graph, gamma. So this means here's some graph, gamma. And on the topological side, this is not just gluing, but this is gluing along a pair of pens. So I'm increasing the number of boundary components by one. And now the upshot of all of this is that if I have two Kitaev graphs, gamma and delta, then first of all, their surfaces with boundary are homeomorphic if and only if these graphs are contained in the same orbit under the action. Moreover, if I want to look at the closed surfaces, then what I have to do is, first I have to increase the number of boundary components of delta artificially by gluing A copies of the annular graph. Then I increase the number of boundary components at gamma by gluing B copies of the annular graph, such that both of these new graphs now have the same number of boundary components, and then I use what I had before. So these new things should now be in the same orbit under the group action. Which means we now have complete control over the topology. It's group action plus this grouping procedure. Even better, the proof is explicit. So what it does is it shows that every orbit contains one of those unique standard graphs, which are more or less generators of the fundamental group. And the takeaway from this picture should be the following. You have the left half, which is just loops which are intersecting. This is for every hole in the torus. Yeah, and then you have things which just contribute to the boundaries, which are these yellow parts here, which are just copies of this annular graph. So if we want to understand surfaces without boundary, we want to have a way to remove these, whatever is on the right. That's the big upshot. Go to the standard graphs, figure out what the annular graphs are doing. That's the whole story.
How do you get the group G?
Okay. It's where did I put it here? Okay, let me try to give you a hint of the real answer. So what I've been telling you so far, everything has been a lie, and you caught that correctly, because while I draw nice pictures, these graphs for us are certain elements in an infinite cyclic group, symmetric group, sorry. This is more horrible to work with, but it gives you ways of doing things which with these pictures you maybe can't do. So the point now is that such an edge, for example, would be a pair of numbers, like 1 and 2, and flipping an edge would simply mean I'm going to the pair 2, 1, which is a tuple. So the order matters, and now the action is precisely that. And that's sort of telling you what the group structure here is. It's a certain cycle acting on this specific cycle, modeling the edge. And
the combinatorics of the graph, and then you can construct a
Yeah.
group that is always unique, or
I mean, there's a big group which is acting on the collection of all of these graphs. It's not fixing the graph, it's going from one graph to a different graph. That's the idea. And you have to choose a nice class. It's not unique representatives of these Kitaev graphs, but it's a small enough class on which this group now acts with nice properties. It's sort of really working out how to model them nicely using group structures. That's what this story really is about. I should say, it's a good point you're raising, though. We want this, so what the relations should be, and we prove it works. That's a very naive approach to this. And we see some hints. So this slide action here is very closely related to mapping class group actions. Again, I can show this in a picture. So let's take our favorite annular graph again, which was just this picture. And the claim was I can slide an edge along another edge. No? So stay in the notation I have here. I didn't put numbers, but I have colors. It's, I think for now I'm fine. So let's put yellow here. And let's put blue here. And now I can slide yellow along blue. Okay, let's do this. So what I'm doing is I'm going closer to blue and then I'm moving along blue. Okay? Here. And what is this? This is the Dean twist along the blue loop. No? So this edge slide, this specific edge slide here, models a Dean twist. There's a more precise relation. So for surfaces with one boundary component, there's a very precise way to make to work this out. For general surface, there's a conjectural relation between these edge slides and certain presentation of the mapping class groups. That they give you a presentation of the mapping class groups. And our group G isn't quite the mapping class group. It has some relations which you wouldn't expect in the mapping class group, but it's closely related. We don't know what the precise relations is, but if you work with mapping class groups, this would be very much interesting to see how to properly write this group G. It does the job for us, but it's not the best choice by a long stretch. There's much improvement to do at this end.
Please remind me what's the definition of mapping class group in this context, because I know for hyperbolic manifolds, but not here.
It's for example, you take the fundamental group of the homomorphisms, so homotopy classes of homomorphisms. Right. That's okay. So let's summarize. What we did so far is we started with this combinatorics, these Kitaev graphs. We found out they give rise to two-dimensional spaces, and we have complete control over how the topology works, because this is governed by A, the group action, and B, this gluing of these funny annular graphs. And now we want to construct a representation theoretic side picture, and we want to follow as closely as possible the classical story. So we want to arrive at a Jetter-Drinfeld module something with these A and B operators. That's the idea. Now, to probably make the physicists a bit less happy, H will be finite dimensional. I should say I don't think really it needs to be finite dimensional. This is just what we did because we didn't distribute to our story. So we could probably put any Hopf algebra here. I'm not 100% certain at this point, but it should work. And you can take any field. You're free to take the complex numbers, but any field works. What we've seen classically is we were putting a copy of the group algebra of Z2 on every edge, and we were acting by multiplication and by co-multiplication. And if we wanted to flip the direction, so going from L plus to L minus, we were using the antipode. However, this is a big problem if we want to go to non-semisimple land, because the square of the antipode is the identity. And if we already also know that H is the dimension is invertible in our field, and this is equivalent to the Hopf algebra being semisimple and co-semisimple. Even worse, over the complex numbers, three things are equivalent: being semisimple, being co-semisimple, and S squared being the identity. So if we want this story, we cannot possibly leave semisimple land. We need something new here. And that's where these, involutive Hopf bimodules enter the picture.
Very quickly, what is a bimodule, bicomodule? Is it a tetramodule or?
Yes.
Okay.
Yeah. It's precisely that. So here it is in its whole beauty. So what we want, we just take what we have in the classical case and we rewrite everything such that we can relax the condition of the antipode needs to be the involution. So what do we want? We want some space, which we can put on an edge, M. We want to be able to act on the left. We want to be able to act on the right. We want to be able to co-act on the left because it has a left face, and we want to be able to co-act on the right because my graph, this edge, has a right face. And all these things should be compatible, so they should be like a Hopf tetramodule, Hopf module on both sides, except we have to twist this a bit using this s to the power minus 2 here to make things work. Plus, I'm always clicking the wrong button. Plus, we want this involution, which allows us to flip the orientation of the edges. And this is just okay. This looks hopefully sufficiently weird. So
-2 on the right, but no antipode on the left. I mean, there should be some symmetry, right?
Yes. Let me come to that in 1 second, and then later in the talk again. Okay. But I don't have a very good answer to it. I fear it works.
Kind of a dual notion where it's on the left.
Yeah, that will happen now, but it will be mysterious. It's mysterious to me. I don't understand really. We do not understand what's going on. So what's the key? A group-like element P in your Hopf algebra. You choose a multiplicative character, one-dimensional representation chi. You ask that if I evaluate my character at P, I get 1, and I have this condition, which is the condition of a parent involution. The square of the antipode is given by the combined adjoint action of the group-like and the character. Okay. And then I can define on my vector space H the structure of an involutive Hopf bimodule by saying, well, the left action is regular. It's just multiplication by G. The left co-action is regular. It's just co-multiplication. And I twist the right actions and right co-actions using my group-like and my character. And then the involution is this twisted version of the antipode. Okay, and if you come from this Hopf cyclic homology, you think, this is pairs and involution, modular pairs and involution. In fact, these are the coefficients of Hopf cyclic homology. Maybe there's a different version to this. And it turns out, this is now going to your question, that's very much true. So if we would go back 2 slides and every copy of the antipode we would replace by its inverse, then we get a nice embedding of these stable Onto-Jeter-Drinfeld modules, which generalize these pairs in involution here, into this involutive S squared Hopf bimodules. However, we cannot work with those because they will not lead to Drinfeld double models in the Kitaev setting. So super interesting, and it does not work for this S to the power -2 setting we have to work with. But something is going on here. We don't have a complete answer to this. It's just a few observations, and it does work. But here's much more to be explored. Also, more interesting example than just this one would be very, very nice to know how they look like. Yeah. Yes.
To stare at the definition.
Yes.
So apply the co-unit on the third tensor factor.
Yes.
Then this should tell you that M is a usual Hopf module on the left.
Yes.
Okay, and if you apply epsilon on the first tensor, this tells you it is kind of a Hopf module.
Yeah.
But you have this S -2.
Yes.
So is this, but it is not saying that it is a Hopf module where you endow H with the coaction on itself given S -2.
There's a fun so what you're hinting at is this reconstruction, right? Hopf modules are the same as are equivalent to the category vector spaces.
No, I don't. At least this was not my intention. But I just wanted to note that this looks very close to a Hopf module or tetra module. But I just wanted to see if you can understand this as -2 by saying, okay, you have H, but endow it not with the usual coproduct, but somehow S -1, S -2 of the coproduct. Coaction.
And just do this on the right. Yeah, I think that's fine. I think that's fine. Yeah, what you can do, I mean, to just state the setting is what you can go to the co-invariance, right? And if you do this for Hopf tetra modules, you do not end up with vector spaces, but Jeter-Drinfeld modules. In this setting, you do not end up with Jeter-Drinfeld modules, but these anti-Jeter-Drinfeld modules, at least up to an equivalence. However, you have this extra structure, this involution, and you have to ask under this identification what happens to the involution. And while you can, Redford's S4 formula tells you so, you can always replace this here by any other, you can always add multiples of 4 to this number, and it does not change your category in an essential way. They are all equivalent by Redford's S4 formula. However, they do something with this involution, and that's why this funny story between going from S to S inverse and vice versa has a different setting. So if you plug in here S squared instead of S to the power -2, and here inverses of S to the stability condition on anti-Drinfeld modules.
Interesting.
So it's quite interesting that you have this equivalence of categories, but if you take the involutions into account, it's a more subtle picture. How to express this nicely and how to generalize this, I really do not know. Okay, so we have these guys. We have at least one example, but obviously we could now ask, is there a nice theory? And the answer is yes. I can define an algebra such that the modules of this algebra correspond precisely to this involutive Hopf bimodules. And I don't want to give you the whole algebra structure, but I think I'm hinting at how to construct it here. The underlying vector spaces, there's a copy of the group algebra of set 2. That's acting by the involution. That's just then I have H tensor H op, right? This models bimodules, and because I'm in finite dimensional land, I can take H dual intertwine all these structures correctly. That's sort of the exercise here, but this is the algebra. So you can build lots of examples. But how to get nice examples, how to find a nicer, smaller algebra, something like the Drinfeld double, it's not really that worked out. We did some work in that direction, but it's far from being a conclusive answer. So
this looks like the double of the double, right? So
yeah. Yeah, I mean, what you can do is you can write down Hopf bimodules as sort of a generalized Heisenberg double, which is you kill this copy for a second, and you can say, well, you want to write down bimodules plus bicomodules and some compatibility structure, which is just these 4 spaces with the correct multiplication. This you can do. But obviously, you would rather talk about Jeter-Drinfeld modules and the Drinfeld double than some weird 4-fold power of some vector space.
Here it's important that H is finite dimensional.
Yes, here it's very much important that H is finite dimensional. So I'm not sure what the answer is in general. So yeah, but as I said, this is half the talk as a pitch of do things which hopefully you find interesting. Lots of loose ends.
And this thing has no Hopf algebra, co-algebra structure.
I don't know. I would expect it's a co-module algebra. The reason being, so what we know is that this category, if we forget about this involution, then we have these Hopf bimodules. Let's call them, I don't know, HM. And they are s to the power -2 twisted. So what they are is a weird way of saying I'm having these anti-Jeter-Drinfeld modules, Hayat-Kakali, Rangapur, and I can take usual Hopf modules without s squared. And then I have Jeter-Drinfeld modules. And I have an action of Jeter-Drinfeld modules on the anti-Jeter-Drinfeld modules. Now I can realize these guys also by an algebra which looks like these last 4 terms with a slightly different multiplication. I would expect this is a Hopf algebra. And I would expect that because this here is a module category, I have a co-module algebra structure on this weird thing. Maybe I have to be careful about the kz squared term. So this I don't know, but maybe you can do more operations, so it should have a richer structure, which we definitely did not explore. Right. Yeah, and I should mention, this is very Hopfy, right? So the oidification here is completely unclear how this would work. She's an expert. So
Question. I guess about the existence of a braiding. It's a similar question. To this one.
It has a kind of so the anti-Jeter-Drinfeld modules, they have a kind of braiding. That's correct. That's why you get sort of cyclic operations out of them. That these come from a braiding in a non-trivial manner. What the involution does to that story, I don't know. How much time do I have left, by the way? But okay, very good. So what it means is the following. Assume I take a map and I take an n-fold tensor product of X, and I take a map F going to an anti-Jeter-Drinfeld module which I want to deceptively call A. Then and X for me is a finite dimensional space. Sorry for that. Then what I can do is I can break down by using the co-evaluation dual of X. Now, what this braiding does, what the formulas tell you, you use this usual Jeter-Drinfeld braiding, so co-acting and then acting. This is the braiding operation here. Let me write this as such. But it does do something with the type of dual because you've switched from the right dual to the left dual. Let's write this here. And why is this interesting? Well, now I can use the evaluation here and go up. And I'm landing at X here. So I have a cyclic operation on these home spaces. This is the kind of operation these braidings realize. They're switching left and right duals. But I have no idea what this copy of Z squared does. Okay. Since you guys seem to enjoy this, let me go back and ask a question. These are Hopf modules on the left, right? We all agree. And look what I've written here. Here we have the identity that the right action is completely determined by the left action, but the left action is free because it's a Hopf module, and the right co-action is completely determined by the left action, but it's free because it's a Hopf module. So this seems a very convoluted way of saying, give me a vector space plus my Hopf algebra and some linear morphism, and then your structure. And it's just about solving some linear equations. And I have no idea how this works, what the examples are, what comes out of this story. But it seems very interesting because really this is just about vector spaces with a funny linear map, which allows you to transfer a left action to a right action and a left coaction to a right coaction, which is really just about a regular action. And it's super weird. I have no idea. But yeah. Good. Right. So with these involutive Hopf bimodule fix, what we can do is we can take a graph gamma and we can assign for every edge of the gamma a copy of M, and you take this big tensor power and call it the extended Hilbert space of our model. And as in the previous talk, we want to endow it with an algebraic structure. So we want to define action for the vertices and co-actions for the faces, because we're in finite dimensional land. So this is where finite dimensionality enters to some extent the picture, is that we can write a co-action in terms of an action of the dual algebra. And how do these actions look like? Without giving you a complete definition, let's look at an example. And the idea is, again, these just use local structures. So what I'm doing is I'm taking a small neighborhood of my vertex in this example. And my graph could look whatever it looks like outside this neighborhood. I don't care. I just look at this very small neighborhood. And then I do the following. I start at my cilium. How many edges do I meet? 2. Okay. So I have to use the co-multiplication once. There are 3 edges. I would have to use the co-multiplication twice. If it's 4, 3 times, and so on. And then I have to look at these edges. Are they incoming or are they outgoing? If they're incoming, I'm acting from the left. If they're outgoing, I'm acting from the right. And in order to turn this into a left module, I add the antipode to the picture. And in this way, I assemble my vertex actions as well as the face coactions, which are just dual to this picture. Now, I have a bijection between vertices and faces, so I can tensor over all the vertices copies of my H. Oh, sorry. And I get this big Hopf algebra blackboard H gamma. I have actions, I have coactions, and I can ask for compatibility relations. And that's in the it turns out that my extended Hilbert space is a Jetter-Drinfeld module over this big Hopf algebra blackboard H gamma, which I found really weird because half the time we were now talking about this is not the other Jetter-Drinfeld module, it's an anti-Jetter-Drinfeld module. And now I'm claiming, but here I constructed a Jetter-Drinfeld module. So here's a funny observation that you can put a different braiding on these kinds of guys. And here's how you do it. You take any kind of, and now we're back at your question, you take any kind of Hopf bimodule where just the right-hand side is twisted by whatever you like. And I really do not care whether it's the antipode or something else. It tells you, well, it has a left action, it has a right action. I can use this form of adjoint action to turn this into just a left action. But it also has a left coaction, a right coaction. And if I forget about the right coaction and just use the left coaction, this thing here, then these compatibility conditions of Hopf modules now tell you that this thing with this action and coaction is a Jetter-Drinfeld module, which is a bit weird, but it does work. And the involution, which was part of our datum, always allows us to transform these graphs locally to get this kind of module structure. And this is how you prove you get a Jetter-Drinfeld module. So even though your spaces want to be something else, you sort of force them by a combination of a regular coaction and an adjoint action into a Jetter-Drinfeld module structure. Okay. involutive, it still works. And now we want to combine these two perspectives, topology and representation theory. So the first thing we did was we noticed that we had this structure group acting on our graphs, and they allowed us to transform every graph into a standard graph. And we want to do so on the algebraic side as well. So the theorem we prove is that if I have two graphs, gamma and delta, such that their surfaces with boundary are homeomorphic, then these Jeter-Drinfeld modules I constructed using my involutive Hopf bimodules, they are isomorphic. How to prove this theorem? Well, I have an explicit description of my group in terms of generators and relations. So I just have to check that they lift to this Jeter-Drinfeld module structure. So what's reversing the direction of an edge? This is just applying the involution. This is why it was part of the datum. That's not that interesting. These edge slides are much more interesting. So here I have my edge, the blue one, sorry. Here I have the blue edge and the yellow edge, and I was sliding the yellow edge along the blue edge. And what I will learn this at some point. No, I won't. What happens here is this is modeled by the Galois map. So somehow now the Galois map enters the picture and plays the role of these edge slides, which is super weird. And also, I should mention at this point, I mean, we're doing all of this over the same Hopf algebra and Hopf algebras everywhere, but one is just contributing to the module story, one is contributing to the co-module story. I think there's a much more general picture of this proof here. Maybe later stuff will not work, but I don't think that you have to fix one Hopf algebra and just work with it. There should be some, if you want to include some defects in the picture, you should have different Hopf algebras, for example. So this is a very simplistic version of the picture, and I'm pretty sure you can generalize this in quite funny ways and have fun with this. Okay. And here's the upshot. What we've proven with this theorem is when we want to study invariance of closed surfaces, we can always restrict to these standard graphs because we're working with isomorphic Jeter-Drinfeld modules now, and our only remaining job is to get rid of these yellow loops. Okay. So let's go back to the original definition of our protected space. We already have it here on the board. The ground state of the model is all elements in my extended Hilbert space, which for every phase co-act trivially, and for every vertex, the action is trivial. Now let me rewrite this equation. Saying that the co-action is trivial means I can take the co-invariants, and they are a subspace of my extended Hilbert space. And asking that the action is trivial, I can do this in two steps. I can first quotient by the augmentation ideal, which kills the action, and then I can re-embed this using a section, which works at least in a semi-simple case because this map is given by, I take a class A of M here, and I'm mapping this to the integral acting on M. And this means that my protected space is the image of the composition of I'm first embedding, then I'm projecting, and then I'm embedding again. But my map S is injective. So leaving this out of the picture does not change the dimension of the image. I could just as well say the space I want to look at, my protected space, is just embedding the co-invariants and then projecting onto the quotient by the augmentation ideal. Does not change the dimension of the protected space. And this is how the bi-tensor product will enter the story. Let's now shift gears and make this a bit more fun. What we do is we take X, which is a right module, right co-module, and there's no compatibility conditions whatsoever. And I take N, which is a right module, right co-module, and no compatibility conditions whatsoever. And now here, sorry, this should be ends. In the tech code, it's already end, but apparently it didn't compile the tech code. Sorry for that. Now what I can do is I can take the k-linear tensor product of X and M, and I can project onto the h-linear tensor product, which is just the co-kernel of the difference of the actions. And I can do the dual version, which is I can take the co-tensor product of X and M, which is the kernel of the difference of the co-action, and this is a subspace of X tensor M. And then I have, as in the previous slide, I have this embedding and the projection. I can compose them, and I call the image of their composition the bitensor product of X and, well, M on the slides, we all think it should be N. Good. Now, while the last slide about this should be the protected space was hopefully deceptive, it's not quite true, because I was acting with the integral, and this theoretically could change the co-action. So what you want to prove, this is really giving you the protected space of the classical Kitaev model, and it turns out this works quite nice. It's a quite interesting, I mean, the theorem itself might not be that interesting, but the proof is very much interesting because it relies on some Frobenius algebra structures. And because we work over an arbitrary field, it turns out that H being semi-simple and co-unimodular, which means this element A here, which measures how far the co-integral is away from being a two-sided co-integral. So if A is the unit, meaning a co-integral is a left and a right co-integral at the same time, then I have a natural isomorphism between these bitensor product and invariant subspaces, where N now has to be a Jeter-Drinfeld module. Why I'm saying this is one question I'm quite interested in, but I have no good answer to, is I would like to know whether my bitensor product is a half-exact functor. If this would be the case, then this theorem would tell us some consequences about the fourth power of the antipode, which is interesting in characteristic greater than 0. But I have no clue. So if anybody of you figures out the bitensor product has to be how to call this, half-exact, then I would be very much interested. I worked a bit on this question. I didn't get a good answer, but it's really interesting. The upshot for us is these bitensor products capture the semi-simple setting, but they are more general. They also work in the non-semi-simple setting. Okay. The way we want to use this bitensor product is we want to interpret them as closing boundaries by gluing in disks, and these disks are now labeled for us with the coefficients we can attach in this bitensor product. For example, here in this picture, this was the graph I've shown in the beginning. I'm closing one of these two boundaries of the torus by gluing in a coefficient called X, which means I'm taking at my favorite blue vertex the bitensor product between X and my extended Hilbert space. Okay, so let's look at the easiest example, which is always we're coming back to the annular graph. There's no way of getting away from it, it feels. What we can do is the annular graph models the annulars. So far, so non-interesting. But if I close one boundary component of the annular, I get a disk, which is a contractible space. And being a contractible space for us should mean it's sort of adding trivial information. Now, we have to transfer this to the algebraic setting. See here, right? We have the annulars here by the annular graph, and it has these 2 points, the inner one and the outer one, the inner vertex and the outer vertex. And we take now the bitensor product just with the inner vertex, which we think of closing this inner boundary. So the algebraic structure with respect to the outer vertex still exists. So it's a Jeter-Drinfeld module over the outer vertex. But the space here on the right is contractible, and the algebraic analog of being contractible, of having trivial information in a monoidal category, is it should be the monoidal unit of your category, i.e. it's the trivial Jeter-Drinfeld module. This is the requirement we're after. If you close the inner boundary of the annular graph using this bitensor product, you should get the module. This is just a heuristic, but we can work with that idea. And what happens is that you can completely, well, not classify, but you can give an equivalence when this is true. Namely, this holds if and only if the co-invariants of my Hopf bimodule are one-dimensional, i.e. they have to come from this pair in involution. No? So from now on, we want to work in a setting where the annular graph only adds trivial information. We assume that the dimension of the co-invariants of M is 1, and we fix such a Y which trivializes this boundary component. I should add, I think that Y should be more or less unique. There's some good evidence, but I don't have a complete proof for that. There's always a smart choice you can make for this why, but we don't have a conclusive answer whether it's unique or not. Okay. And I should say, there are counterexamples where Hopf algebras do not admit a Hopf module with this structure. So there's a slight restriction here. I should say these examples so far have all been rather esoteric. Okay. And now I'm taking coefficients for my model by attaching something for every vertex, for every boundary component. And basically what I'm saying is, what I'm saying is the following. You give me, choose what you like, and then I'm taking again a big tensor product indexed by the vertices of my graph, where I put x at my body, at my favorite vertex, there's x, and everywhere else I use this y, which trivializes the annular graph. And then I'm defining these topologically, or to be topologically protected spaces, to just be the bitensor product between blackboard x gamma, blackboard m gamma, over my big Hopf algebra blackboard h gamma. And in case x is the trivial right module, right co-module, we call this the ground state of our system. And now we want to prove this is a topological invariant. And the way you prove something is a topological invariant, if you come from algebraic topologies, you should find some version of my view torus. And this is what we're trying to model here. So what's going on? We take two graphs, gamma and delta. We take two coefficients, x and x prime, and then we construct this auxiliary space, which is again a bitensor product, but a slightly more complicated one. So I'm not giving you the precise definition here. And the upshot is that we can take the tensor product of these protected spaces, and this is an embedding, a canonical embedding in this auxiliary space. And we can take the bitensor product between the gluings of these graphs with coefficients, tensor product of x and x prime, and it has a canonical projection onto this auxiliary space. And why is this interesting? Well, we're working over vector spaces. So over vector spaces, I can choose a section of pi. Might not be a canonical section, but I can choose one, which means I have a non-canonical embedding of what's on the left-hand side into that what's on the right-hand side. And I want to prove this is an isomorphism, at least in good cases. And this is precisely, we should stay on this slide. This is precisely what happens if I plug in here for my delta, I plug in the annular graph, and for my x prime, I plug in the trivial Jeter-Drinfeld module, the trivial right module, right co-module. Then the map K and the map pi are isomorphisms. I compose them and I get an isomorphism between the protected space of here associated to gamma. This protected space is one-dimensional, so it does vanish, and the protected space of the gluing of gamma and the annular graph, which means the protected spaces do not see copies of the annular graph. And the consequence is that these protected spaces are now topological invariants. If I have two graphs which parameterize homeomorphic surfaces, closed surfaces, then these protected spaces are isomorphic vector spaces. And this completes our picture here. So now we have this common demeanor between topology and representation theory. I guess, how much time do I have? 0.5, whatever. Okay, then let's not stop here. Let me be a bit quicker for the last 5 minutes, but I think I should mention some connections to geometry, because so far I did a lot of Hopf algebra mumbo jumbo, but you would like to see nicer examples. It's still the finite group case, but I'm pretty sure you can move away from finite group and then it gets more interesting. What I want to do is the following. I fix a number G, any natural number including 0, and I define this group omega1 of sigma G. Right? These are just symbols now. In the case G equals 0, I take it to be the integers. Otherwise, I'm more or less writing down the fundamental group, except these iterated commutators, this product of commutators, which in the fundamental group of a surface of genus G should be trivial, are now X. So I'm taking a central extension of the fundamental group of a surface of genus G, and I call this omega1. And a small remark: such groups arise in the study of three manifolds from Seifert fibered spaces. I don't know anything about those. Okay, why is this interesting? I can look at the set of group homomorphisms from this central extension into any fixed finite group G. I can linearize the set, and then it has a Jeter-Drinfeld module structure. The coaction is just measuring where this generator of set in my central extension is landing. That's the coaction here. Let me maybe go back one slide. We had always this generator X here, which was in the center, and it's just measuring where my X goes, and the action is just the adjoint action on the group, extended here on these morphisms. So what I can do, because there's a Jeter-Drinfeld module over a group algebra, I can decompose it as a co-module, and I can say in degree P, for P an element in my group, it has these elements. I really did not compile the file, sorry for that. There should not be a D in the end here. Okay, why do we do this? It turns out these coefficients I can choose for the Kitaev model, they come from a central element in my group P and the multiplicative character, if you're in Hopf algebra language, of my group algebra. So for those guys, I find a suitable involutive Hopf bimodule for any of those. It's a one-to-one correspondence. And now I can ask, what is the ground state of my module? Ground state is just I take this Jeter-Drinfeld module, I take the degree P to the power 2G part, and I quotient by this adjoint action and twist this character. Now this does look horrible. It's just a computation to check this is correct, but nothing is preventing us taking the group and the character to be trivial. If we do so, then we get the following nice space. Then we get the span of what's called the character variety, which is just to take these group homomorphisms from the fundamental group, because X is now trivial, so the central extension is vanishing. I'm just taking the group homomorphisms and I'm taking the orbit set under the adjoint action or conjugation action of the group. And this is the protected space. And people who come more from the geometric side of this model tell me this is closely related to flat connections and that kind of business. I don't know that much about this, but I would be very much interested. I guess this is more up your alley to hear where stuff like this appears in your setting. So, but I think I want to end with this. So it turns out in the group case, we see something which looks like character varieties and which has some connections, even in non-semisimple cases. There's no assumptions, again, on my field, which is more closely related to some geometric questions. Okay, and yeah, that's a good point to solve this.
Yeah, thank you for this great talk. Are there questions?
Modules going around. I mean, is this associated braiding symmetric? Does it square to the identity in any case? Never, always. Sometimes.
No. Does not. It doesn't have to. No.
And since you're in Marburg, then what does the associated Nichols algebra look like? Is it finite dimensional?
I have to admit I do not work with Nichols algebras. I have no idea. Let me. So I think the only reasonable answer I can give is this will you have some freedom in the Jeter-Drinfeld modules you're going to construct in this way, but you will not get arbitrary Jeter-Drinfeld modules. So we're not seeing all of them. There are some nice ones. I mean, if you work out what happens in the group case, I mean, we just erase this one. So what happens in group case is I can take this graph, and this is parameterizing the torus. So it has two copies of my group algebra, but now viewed as a Jetta-Drinfeld module. And let's see what the Jetta-Drinfeld module structure is. So this is sort of the paradigmatic example of how things will always work. This is the nicer joke, right?
Yeah.
Oh, yeah. Oh wow. Oh, I have to be careful. So the story is, this is my cilium, and I have now to move along this path and see how I encounter edges. So what I do, I start here, and I'm moving in the direction of A, which means I get a, let's write this as an A minus 1. I take the left coadjuvant, which is here because this is the trivial example, it's just co-multiplication. We're going to fix the indices afterwards. Now, I'm moving here, and I'm back at my original vertex. Now, what I have to do is, for the vertex actions, I was turning counterclockwise. For the phase actions, because I do a left Jetta-Drinfeld module, I have to turn clockwise, and which brings me to B, but now I'm moving against the direction of B. So I have to put the right action of B here and the antipode here. Okay. And now I'm here back at my vertex. I turn clockwise, and I'm back at A, but now I'm moving counterclockwise. One here. And finally, I'm here, I have to turn counterclockwise. I'm moving with B, and I'm back to the start. So this is B minus 1. Then we have to tensor with A0, cancel B0. Now, this tells me this is B1, which is because we're in a group algebra, it's just B. This is S of A1, but we're in a group algebra, this is just A inverse. Then this is B inverse, and this is A inverse, tensor A, tensor B. Sorry? Yeah, this is just A, exactly. And this is the commutator bracket of B and A inverse, right? So this is why the commutator brackets were appearing at the end of the talk. This is the module structure. I'll just tell you verbally. There's no much point in working this. I will act here on the left with H, but I will also act here on the right with H inverse. Now this is a commutative group, at least in a nice setting. So I'm not doing anything. My action acting on A tensor B. In full generality, this will be H A H inverse tensor H B H inverse. And if we're in the abelian cases, just H tensor B, where H is a group-like element in, let's put a group-like here in my group algebra. So these are the kinds of Jetta-Drinfeld modules we're studying, which is still nice, but maybe not canonical examples in this sense. So I have no idea what is happening here. However, to give you a different answer to the kind of question it's not precisely an answer to your question, but I guess the connection you would like to see is something with exterior algebras, for example, right? And here's something which, and again, this is a pitch of things I don't understand. We understand some stuff, but 90% we don't understand. We just figured out we don't understand them. It's the following. So in a semi-simple case, we want to use the integral to define projectives. Now you can say, okay, fair enough. Let's take our picture and assume the Hopf algebra is finite dimension, semi-simple, and just push it along as far as you like. Now, Still semi-simple, but we want to use this, let's call it the annular approach. So really centering everything around. Once you understand the annular graph, you go. What we want is, we want to trivialize this graph here. I want to draw it in this direction. From the semi, you should act trivially and you should coact trivially. Now, to coact trivially, you can work out that it very much makes sense to put a 1 here. So this should be something I want to associate to this graph now, something in H tensor H, and let me actually write this as H loop tensor H spike. So I have this spike in the middle and I have the loop 2 copies, and I want to associate something nice. I can take a unit here. This will give me more or less a trivial coaction. There's some checks to do, but it does work. And you want to put something here which has trivial action. And there's the one choice you can make, which is the integral. And this works in the semi-simple setting. It works in general because the integral does have very nice properties in the semi-simple setting. It does not have those in the non-semi-simple setting. So I said exterior algebra. So far, I've been talking about Hopf algebras exclusively. Let's change this. Let's kill this part. What I have to do is I have to substitute the integral for the only other nice element I know every Hopf algebra has, which is the unit. And then this works again. This is how you trivialize. If you look under the hood, how we trivialize this. This is by placing here the unit and here the unit, and show that everything is in the isomorphism class of this element, in the equivalence class of this element. Now, why I said exterior algebra is, if you think about the Nichols algebra perspective, so you have some Nichols algebra which is finite dimensional. So this is a finite dimensional Jeter-Grünfeld module over a Hopf algebra H. I can think of the bosonization, and I will do this the wrong way around. And it turns out this thing is graded. Yeah. And I can ask, where's the integral? So let's say this is A. So A is a direct sum going from I equals 0 up to some number n AI. The trivial observation to be made is 1 is in A0. It's a trivial component, and the integral is in the top degree part, right? It comes from the one-dimensional top degree term of my Nichols algebra plus the integral of H. So we think of this. This is some top degree part of this plus the integral of H. Now, but here's the interesting thing. If I look at my Nichols algebra, I have this one-dimensional space. BV0, and I have BVN here. And if this were an exterior algebra, I have a nice duality between these bases, right, which is Hodge duality. And now I'm telling you the integral, which I use in the semi-simple world, is in top degree part, but it doesn't work. I have to take something from the bottom degree part. I have to go to the... I don't know whether there's a nice duality going on, which I think is true, because what we're using under the hood is a duality on these kinds of graphs, right? We have the vertices and we have the faces. There's some kind of Poincaré duality encoded in these graphs. And this seems to play a role in passing from integrals to the unit. because the unit is here sort of functioning as a substitute for the integral in a weird way, which seems connected to this story. I don't know what's going on here. It does work. That's great. But again, there's a lot of things you can do here and have fun and understand what's really going on.
Over time, so if the short question, we still have time for that. Maybe from the online people, someone has a question. If it's not the case, then let's thank the speaker. And yep, see you guys again in autumn. Yeah, thanks.
So the first talk on October 7th is Peter Zeman from Caroline.